Hello, I'm Teddy Wanker. So today I will show you guys the step to actually build a circuit like this to convert the AC voltage to the DC voltage. And the best part is this is the DC dual rail power supply, so you actually have two rail like this, not just one. So the concept behind is we actually want to convert the AC voltage from our power outlet. Right now I'm living in Australia, so my power outlet is providing 230 AC voltage with the frequency is 50 Hertz. And we actually want to convert this sine wave AC voltage into the DC source. And we actually need two, one for positive and one for negative. So I choose the value I want is maximum 20 volts plus and negative 20 volts. You can choose whatever you want, it's based on you, but I think 20 is more than enough. So why we need negative voltage and what it is. So let's say you have an op-amp right here. This is the op-amp operational amplifier schematic, and this is how it looks in real life. So in order to power it, to operate the op-amp, you need positive voltage and negative voltage to amplify the gain, let's say for your audio amplifier. So, and if you really want to create a very simple DC dual rail power supply, let's say from batteries, I can show you how to do it. Let's say you have two batteries, 9 volt, and you want to have positive 9 volt and negative 9 volt. How can we create that? So let's say you connect the battery in series. This is the series connection, and you choose the middle pin as the reference point. So this point would be 0 volt. This is the reference point. So when you choose this pin as the reference point, it would split the voltage into two different voltage sources. One would be plus 9 volt and one would be negative 9 volt. So this is how it looks in real life. You connect the battery in series, so the negative terminal of the battery connect to the other terminal, the plus terminal of another battery, and you let the middle point you put a wire on, and you treat this as the reference point, the blue one as the reference point, and then you have it. The red one is plus 9 volts and the black one is negative 9 volts. So it is based on the reference point. So this is just a simple series connection of two batteries. But let's say I don't want like 9 volts plus 9 volt and negative 9 volt. I want like 18 volt. I just can simply use only two wires like this. We just need to use only red and black, because this is a very basic connection of this, like the series connection. We don't need the reference point right here. We choose the reference point maybe like right here, and then you will have like 18 volt at this terminal and 0 volt at this terminal. It's very basic, like it's based on the reference point you choose. Pretty easy. Okay, but what is positive voltage? As you might know, the positive voltage is just a simple current flow. When you have a battery like this, we have the multimeter right here, we have the battery like this, you put it like this, and you measure the battery, the current flow. It's kind of mess, sorry. So you measure like this, the positive terminal to the red and the negative terminal to the black, you will have the conventional current flow, and this is the positive voltage as we know. But what is negative voltage? So you keep the terminal, like the connection of the multimeter, the same. You just let it sit right here and you just flip the battery direction to this one. You actually get the negative voltage. So let's say I turn this on. So in order to get the positive voltage, the negative terminal, I connect like this, and this is the positive terminal. So as you can see, it's like 4 volt. So this is the positive voltage, and if we flip the terminal of the battery, so I just flip the connection. You can see the negative sign indicates that this is the negative voltage. So basically, what is negative voltage actually like? For me, it's just a simple current flow. So current flow from positive to negative, high potential to lower potential. The current flow would be like this. And for a negative voltage, the current flow just simply reverse like this. So the current is still flow, but based on what we measure, based on the concept, like what we used to measure, it is negative, because since we don't change the connection of our multimeter, I don't know what it is, the pin, whatever. So since we don't change, we get negative value. But if we change it like this, we actually don't get negative value anymore. We actually get a positive. So let's say negative voltage is just conventional current flow, but in reverse direction. Okay, now let's come to our first electronic component, the transformer. What do we need the transformer for? So basically, our AC power source is pretty high. As you can see, the voltage source is a sine wave with 230 volt RMS, pretty high for any circuit to operate. We want to step it out to around like 15 volt RMS. So the transformer is an electronic components that with the primary coil with the main source, we're using 230 volt plug into the primary coil, and in the secondary coil it's gonna output the voltage source, which is already stepped down to our suitable voltage range. And remember, this is dual rail power supply, so we need to choose the transformer which has the center tap option, like this one. I bought it in J-Car, Australia. So this is Power Tech. This is power transformer, pretty heavy. The transformer has the option for the center tap. So it has the option for 30 volt, 24 volt, and 18 volt. So we're gonna use this to generate the positive voltage and negative voltage. So I think this is the last one in the store. So in real life, the transformer looks like this. We have two big ass red wires like this. This is our main AC source, rating from 0 volt to 240 volt. So you plug these two wire in your outlet, your power outlet, and you have to solder the wire with the connection like this. So you have, so you want 30 volt center tap option. So you want to solder one wire to 30 volt pin right here, one wire to 50 volt right here, and one wire to 0 volt. And so basically, if you put a wire like this, this would be our reference point. Remember, this is 15 volt. It's not like negative 50 volt right here. This is our reference point at the 50 volt right here. This is 0 volt, and this is negative voltage. This is negative 15 volt, and this is positive 15 volt, because we already have the reference point at the 15 volt terminal. So this terminal right here would be changed into the reference point 0 volt. This one would be minus 15 volts, and this one would be like plus 15 volts. So this is center tap option. So this is the schematic of the transformer. I will show you. So you have 50 volts output, minus 50 volt output, and you have the reference point in the middle, which is just the same as the real one. Two terminal for the transformer to output, and one terminal for the reference point. All right, I'm gonna expand a little bit about the center tap. So with the center tap, you're gonna split the value into two. So with 30 volt center tap, you have like plus 15 and negative 15. With 40 volt center tap, you have plus 20 and negative 20. So why not choose 20 volt transformer? So this is one of the misunderstanding concept of choosing the transformer. As we already know, we want the output to be plus 20 and negative 20, right? So why don't we choose like 40 volt center tap? It's pretty close to our value, right? Well, it's not. This value is indicated by the square root of the RMS value. So for example, I have the 30 volt center tap. This is plus 50 volts, and this is minus 15 volts. So these are RMS value. Okay, so this is not the peak value. You can see right here, 50 volt is somewhere around here in this line. It's the same as our AC source. 230 volt RMS is around right here. It's not the peak value. The peak value would be the RMS value multiplied by square root of 2. So for the peak value of our AC source, you just need to use the RMS value multiplied by square root of 2. You will get around 325 volt, and this is the peak value. For the 15 volt, if we want to calculate the peak value of the voltage, so we just need to let 15 multiplied by the square root of 2. You're gonna get like 21 volt. So our 30 volt center tap is already generating 21 volt peak value. So we don't need 40 volts center tap, because the square root of 2 multiplied by the RMS value would give the value for the 40 volts center tap close to 30 volts. As you can see right here, this is 28 volts, positive 28 volts and negative 28 volts. So this is pretty high. We don't need it. We need the value to pretty close to 20. So we choose 15. It would be pretty suitable for our calculation. And yeah. All right, let's move to another part. This is rectifier. We're using diode for the rectifier. So first, what is diode? So this is the schematic of the diode. You have something looks like this. This is the polarity of the diode. This is positive terminal and this is negative terminal. So this is how it looks in real life. You will have a silver end right here, indicates the negative terminal of the diode, and so the other end would be positive terminal. And the purpose of the diode, its natural behavior is to block the reverse current flow. So let's say you have the current flow from the high potential to low potential like this. So the current flow like this, right? The current flow is like this, and yeah, nothing happened. Everything is fine, everything is good, pretty, but like let's say somehow you come across something called short circuit or reverse voltage, reverse current. So the polarity is switched. This is the positive and this is negative, and based on the current flow, the conventional current flow, the current flow from high potential to low potential, so the current is trying to flow this way, but luckily we have the diode. The diode will block the reverse current flow up to 1000 volts, and the maximum current rating is 3 amp. So let's say the diode is like your circuit protection. It's like your very last defense. And if you have 4 diodes, you can create something called full bridge rectifier. When you connect like this, you can create something called full bridge rectifier. As you can see, I leave the middle pin right here without any connection. I'm gonna show you later why. And right now, I'm just using 2 pins of the transformer, the plus 15 and the plus 15 right here and the negative 15 right here. So if we connect like this without the middle pin as the reference point, the voltage is gonna be 30 volts in total, and 30 multiplied by square root of 2 is 42.42 volts. So we have 42.42 volts positive and negative 42.42 volts. Okay, is this clear? It's not 15, okay? It's not 15, it's not 21, but 42, okay? Because we don't have the reference point right here. We just simply use the 2-pin connection, so it's 42. Okay, so the purpose of the full bridge rectifier is to flip the negative voltage to positive region. So we just flip it from AC to DC. Yes, this is DC, okay? So DC is just direct current. Anything exists in the positive region without entering the negative region, we can call it DC, okay? So this is DC voltage. And for the frequency, it was 50 hertz, but right now it is 100 hertz. Why? Because now it took like half effort to complete the cycle. So before, this is 1 cycle. So this is 1 cycle, 2 cycle, And right now, this is how it completes one cycle. 1, 2, 3, 4. So it's basically half effort. So the frequency is twice before. And yes, we still keep the voltage, the peak voltage, the same 42.42. Just leave it right here. And I will explain a little bit about how the current flow in this circuit. So let's talk about the current flow in this circuit, in this rectifier. Basically, we have two stages, stage 1 and stage 2. At first, we have the AC power line. The AC is now in the positive region with the peak voltage is 42.42 volt. And first is entering the stage, is entering the circuit. Stage 1, the current will flow like this. This is the AC current flow, and to this circuit right here, this flow like this. We have the load. So if we have the load, the current will flow. The current flow through the load. It flow through D3 and it flow through D1 and back to the source like this. It's kind of hard to see, but you understand the concept. So this is stage 1, the current flow like this without entering D2 and D4, of course. Why? Because you must understand that current is only flow from high potential to low potential. So in stage 1, the current flow like this. Okay, it's not gonna flow like this. It's not, because with D4, this is high potential, and also the same with D2, this is high potential. So it's not gonna flow from this node to here or this node to here. It's not flow like that, because this is a very basic concept of electronic. And so this is stage 1, and now we entering stage 2. So right now, the voltage is in the negative region. So entering the circuit right here, the circuit is the circuit current is like this. This is the current flow from start to end. So right now it's entering D4, and through D4 is entering the load, and after it escaped the load, is trying to get back to the source. It's now entering D2 and then back to the source. So as you can see, from stage 1 to stage 2, stage 1 is keep the positive voltage in the positive region, still the same. And for the stage 2, it flips the negative voltage into the positive region, as you can see, because when we have like oscilloscope, we want to see what is happening with the load. As you can see, the current is still flowing from high potential to low potential in stage 1, which is the same as stage 2, is still flowing from high potential to low potential. So basically, the current through the load is not changed at all. It's still flowing like this. So we already create a circuit to convert AC to DC, okay? And this process only involves 2 diodes I mean, we have two diodes involved in each stage. So therefore, the maximum peak voltage, the output voltage from the load right here is now 42.42 minus 0.7 multiplied by 2. We will have the peak voltage is nearly 41. So before the rectifier, the peak voltage is 42.42, and after the rectifier, after it's entering two stages of the rectifier, the maximum peak voltage is only 41 right now. So there is a voltage drop between the diodes based on the diode. Okay, pretty easy, right? I will explain again for you to understand. So at stage 1, the current flow like this, entering the node right here. So the diode, the diode D2 blocks the current flowing in this direction. So the current's only option is flow through D3, and after it's flow through D3, is entering this node right here, and the diode D4 is trying to block the current flow in this direction. So the current only option again is through this one right here. So we will have the load connection right here. So without the load, there's no current flow, of course. So the load, the currents flow like this, entering the load and escaping the load, and entering this node right here. So this D2 is not blocking the current from flowing, but the current is only flow from high potential to low potential. So right now, the current is in the low potential, and this node right here is high potential. So the current won't flow from this to this because it doesn't make any sense. So the current is flow through D1 because high potential to low potential, and entering this node again, and this node right here, the current won't flow through D4 because the same concept, the current won't flow from low potential to high potential. So the current only path is going this way and to the source. All right, so after we finish the rectifier part, so this is the rectifier, this is my circuit. Now we move to the filter part. We are using capacitors for the filter part, and so I will explain a little bit what is this and what is ripple voltage in related to this concept. So after the rectifier stage, the voltage looks like this, right? But this is DC. I already told you that this is DC, but not so close to our desirable DC voltage, because you know, we want the DC to probably look like this, a straight line, but this is not a straight line. This is half sine wave. So we need something called capacitor. So what is capacitor? Capacitor is an electronic component that store energy and release energy. So this is a capacitor. It has two pins. This is negative sign and this is positive sign, indicates by this label right here, as you can see. And the value for this capacitor is 4,700 microfarad, and the voltage limit for this is 50 volt, pretty high. So this capacitor is used to charge, and used to store and release energy, or charge and discharge. So okay, so in order to understand how the capacitor behave, I will help you to understand the concept of this capacitor right here. So we have a circuit like this one. We have the battery, the switch, a capacitor, and another switch which is open, and a load right here. So in this stage, the battery is trying to push the current flowing like this, right? Because this switch is closed, so it creates the path for the current to flow, and the current flow to this, entering the capacitor. So basically the current is flow like this, and the current, well, I mean, I can say yes, the current can flow like this, but it's only like pretty fast, like just a blink of an eye. The current is flowing like this, and this is like a closed loop, and there's nothing to do with this loop right here. And so if we open the switch, this is stage 2, there's no current flow from here to here, right? The capacitor will now release its stored energy, release the charge, release the energy, and the current will flow this way through the load and back to the source. So as you can see, basically capacitor is an electronic component that store energy. So it store the energy from the battery, and then it release the energy to the load. And so you can say capacitor is basically like a battery, but it can release energy pretty fast. And now remember, so we already have 41 volts peak voltage. So in order to connect the capacitor like this, so this is the negative sign, this is positive sign, we must choose the capacitor with the voltage rating higher than the peak voltage. So this is 41, I choose the capacitor with 50 volt. So really 50 volt is not safe, you know, you should choose something like 60 or 70 volt, but I accept the risk, so 50 is enough. Remember, choose the capacitor with the higher voltage rating of your design, okay? So with the capacitor between two rail like this, the voltage is now changed from the half sine wave to this straight line right here. But actually this is not our desirable straight line, because this is our desirable straight line, and this is kind of like serration line, and it's not what we wanted. But we can fix that by adding more capacitor or increasing the value of our capacitor. So to talk a little bit about the filtering stage, what is happening inside this stage. So let's zoom in. We have something called ripple voltage. So for example, this is the waveform without the capacitor, and when we add the capacitor between these rail right here, this is the time that this capacitor charge or store its energy. So it store the energy from here to here, and this is the peak voltage. And at this moment, the capacitor release its energy because the voltage now is trying to decrease, and the capacitor is releasing its energy to in order to keep the voltage still high, I guess. So this stage from here to here, the capacitor is store its energy, and from here to here, as you can see, the capacitor is discharging. So it creates something called ripple voltage, and when we zoom out, the ripple voltage is basically look like this acceleration line. So it's good. It's not a straight line, but we can accept that. But if we want the acceleration line close to the straight line as possible, we just need to increase the value of the capacitor. But how can we increase that? How can we minimize the ripple voltage? How can we make it like pretty close to the straight line? So this is the formula for the capacitor. How can we choose? So we already have the frequency before 100 hertz. We have it by calculated, and we now need to calculate the time for it to complete a cycle. So this is the formula for the time to complete a cycle. So it takes like 0.01 second to complete the cycle, and we plug it in this equation right here. This is the equation to find the value for our capacitor. So let's say assuming that it is constant load current. The current is 1 amp, and the ripple voltage allowed is 0.5 volts. So we can allow the ripple voltage is 0.5 volts. Right here, the potential difference between here to here is 0.5 volts. It is acceptable. Many people want it to be like 0.1. I don't care, because this is like just like a custom project. It's in my lab. It's not used for precise machine, so 0.5 is enough. And then we have the, but something is not correct in here. Let me check it again. So this is not 0.01, this is 0.5, sorry. So plug it in. We have the time is 0.01 right here. We have the current allowed is 1, and the ripple voltage is 0.5 right here. And when we plug it into our calculation, we have 0.02 farad, which is 20,000 microfarad. And based on like basic calculation of capacitor, if we want 20,000 microfarad, we need something like 4 to 5 of these capacitor. So with 4 we have something close 18,800. With 5 would be good, but actually we just don't need that much. We can say we can only use 2. It would be enough. For me, for my project, I use like 2 capacitor for positive rail and 2 capacitor for negative rail. So in real life, so this is only in theory, okay? So in real life, for my circuit, I use 2 capacitor. So we need to plug it in again. So 2 would be like this, 4,700 microfarad capacitor equal the constant load current allowed is 1 multiplied by the time for it to complete a cycle, and divide by the ripple voltage, which we don't know yet, because in real life it's different. So we make it a no. So right now the ripple voltage is 1 volt, pretty high. But again, I don't care. It's just a basic circuit, and I don't use it much, so doesn't need for a precise circuit. As you can see, our ripple voltage is pretty high. It's 1 volt different. So if you want something close to a straight line, you should add more capacitor in it, or you should choose one gigantic value for your capacitor. And remember to check the voltage rating of your capacitor. For me is 50 to avoiding explosion. Okay, so just to be clear, this is on theory paperwork and this is real life. So in real life, I only have two 4700 capacitor, so the value for my capacitor is only 9400. Pretty far from the theory because I don't have enough capacitor to actually create that desirable value, but it's enough for me, you know. So the question is why we actually need to minimize the ripple voltage as small as possible. So let's say you have 41 peak voltage, I mean 41 DC voltage right here, and the actual voltage you might get is 40 to 41. Okay, so it's not a constant value. It might change a little bit, around 1 volt. So we need to actually minimize the ripple voltage as small as possible. Okay, so now we move to the most important part and also the final part of this DC power supply, the regulator part. As you can see, in the real circuit, after the filter stage using capacitor, now we're entering the stage with the regulator using two bipolar junction transistor. So we are using one LM317 right here. This is for positive voltage regulator, and this is LM337 is for negative voltage regulator. So let's talk about what is regulator first. So the purpose of the regulator is trying to stabilize the fluctuating voltage into a straight line, a stable line, a stable voltage. So let's say you have the voltage range minimum is around like 40 volt right here, and the peak is around 70 volts right here. So the voltage is not a straight line, it's fluctuating up and down, and you don't want it. You want a stable source, a stable voltage source. So you're trying to stable it using a regulator. So this LM317 and LM337 is trying to keep the voltage constant. So let's say you have the minimum is 40 and maximum is 70. The output voltage will always trying to be around like 35 volts, for example. So it's always constant, and this is a very good source, a good way to stabilize the voltage. And some might trying to say that why we need the filter stage, like why we need the capacitor stage instead of just using the regulator stage. So I understand what you mean, but so the oh, actually wrong paper, just the back. So as you can see, why don't we just add the voltage regulator in this stage instead of the filter? Because as I for the regulators can only generate the output voltage lower than the input voltage. So if you, for example, if you have this halfway sign right here, the input voltage, so the voltage is not always constant. It's changing from like 0 volt to all the way up to 41 volt. The regulator cannot output this kind of voltage like constantly too, because it can only output the voltage lower than the input. So we still need the filter stage. We only need the filter stage to keep the voltage more than, like, for example, 40 volts, and then we will use the regulators to step it down and trying to create a constant value that can be adjustable. So again, there are rules of the regulators. First, there is crucial dropout voltage. For the LM317, the maximum dropout voltage can be 2.5 volt, and for the LM337, the maximum dropout voltage can be around nearly 3 volts. So it's mean like if you input 6 volt right here in the input channel, right here in the input terminal, the output can only generate like 3 volts. Okay, 3 to 4, I don't know, is around that. Okay, so again, the next rule is the regulators can only generate the output voltage lower than the input voltage, remember. So you always trying to feed the input voltage higher than your desired output voltage. Okay, so after we have the formula to control the output voltage, first we need to find the fixed resistor value for R1. So let's say we want R1 to be around 240 for both. So 240, and R2 will be the resistor that value can be changed. So what kind of resistor that value can be changed? It is the potentiometer, right? So this is potentiometer. Also the same with this one, potentiometer. So let's say I'm using potentiometer with 5K. This means that this potentiometer resistance can vary from 0 to 5,000 ohm. So let's say I have the formula right here for the positive voltage regulator. So we don't need to put the I adjustment into the equation because we put the I equal to 0, so 0 multiplied by R2 is 0, so we don't need to put it in the calculator. And so we have the fixed value R1 right here is 240, and the R2 is potentiometer. So first, let's talk about the potentiometer. Potentiometer has two different types of using. First, we have the voltage divider using all three terminals to provide a variable voltage output. And the second is the variable resistor mode. So we only need to use like 2 pin right here. So instead of using in total 3 to create the voltage divider, we only need to use 2 because right here this is resistor. We only need to control the current flow, minimize the current flow or increase the current flow. So 2 pins is enough. Remember, only use 2 pin, not 3. Okay. Some people can use 3, but I recommend 2. 2 is enough. So put the equation in. Now put a value in. So let's say my potentiometer is all the way down to 0. So I twist the potential all the way to 0. So put a 0 in the equation, and then we have 1.25, which is pretty close to the output minimum voltage, as you can see. But if we increase, like if we twist the potentiometer like half value, like 2,500, the output is around nearly like 14. So if we increase 8,000, you can see 16, nearly 17, and all the way up to 5,000. So this is the output, as you can see. So for me, we don't actually need to output all the way to 37 because in our circuits 20 is mostly enough. 20, 21. So I select 5K and the fixed resistor is 240. Now this part is not so important, but you can add it if you want it. This is diode protection and noise filter. So right here, this is LM317 and this is LM337. So actually, first let's talk about these two capacitors right here. So this is a very small value, 1 microfarad, and this is even smaller, 0.1 microfarad. This is the capacitor C1 and this is capacitor C2, let's say, and this is C1, C2. Okay, so why I add C1 and C2 in this circuit? So actually C1 is requiring if the regulator is located more than 4 inches from the power supply. So actually you don't need C1 if your regulator is close to your main power supply source. So this the circuit is pretty close. You actually don't need this one right here. This is C1, as you can see. The yellow one is C1. Actually, you don't need it. I just put it in for fun. And you only need it if the regulator, this one, is far from the source. So the regulator is far from the capacitor, the diodes. So actually, you don't need it. And secondly is the C2. So C2 is necessary for stability. But you actually don't need it to, because the output might be somehow fluctuating a little bit, and this C2 exists to stable the signal, the output voltage, but actually you still don't need it. But I still put it in. As you can see, this is C2. For C2, I put 2 C2, so this is C21, C22. So for the positive range, as you can see, this is the regulator, this is the C1, and I have 2 C2 for this rail right here. I just put it in, and okay, so move to the LM337. It's basically the same. You can choose like 0.1 microfarad and 1 microfarad. It's not so important because we're not working with very precise a signal. So same concept. If C1 is, if the regulator is pretty far from the source, then you need C1. But rather than that, C1 is not needed. Also with C2 is only for stabilize the signal. Without it, the signal is kind of disturbing, but it's not so important for real. So capacitor is not so important. This chapter is like an extra theory to put it in based on the manufacturer recommend. Okay, so let's talk about the diode. You can see 2 diodes, one for the LM317 and one for the LM337. So these diodes exist to protect the source circuit. So let's say when you have a load right here, the output, then when you connect the load, and then the C2 is working, the C2 is charged, and then somehow you release the load, C2 is still charging, but there's no path for C2 to release its charge. So C2 might trying to move the charge. Instead of going this way, C2 is trying to move the charge this way. so it's trying to damage the output of the IC right here. So this path right here, this diode is for C2 to move the current to this path right here and entering this input, and then the charge is going from the input to the output safely without damaging the IC. So this is basically like a path. You can choose whatever diode you want. For me, 1N4007 is enough. Some people might choose 1N4002. I don't care, just pick whatever value you wanted as long as it is suitable for your project. It is the same concept with the LM337. You put a diode right here, and remember to place the diode correctly like this to protect your IC. You should not flip the direction of your diode, remember. Just follow the instruction on the manufacturer. Now I will trying to read the datasheet with you and explain a little bit.
All right, so let's talk about the datasheet of the voltage regulators. So we have the positive LM317 and the negative LM337. I will put these datasheets in the description for you to take a look at. Right now, I will explain a little bit. So actually, just like I said before, these ICs are basically the same, but in opposite way of how it operates. So you just need to understand one, then you can also understand the behavior of another one. So right now you can see there are like 13 pages. Actually, you don't need to read all the pages. You just need to take a look at some specific page. For example, like the first page, you have the maximum current rating, 1.5 amps. So remember, if your project require more current to operate, this I say is not enough. Same concept with the negative regulator right here. The output current is only can around like 1.5 amp. So choose wisely. Okay, so next we have the schematic of the regulator on paper. We have R1 and R2, very familiar, and we have input capacitor and output capacitor. So you actually only need to put the input capacitor if the regulator is far from the power supply. So this is only to filter the noise. You actually don't need this if your regulator is placed pretty near from the filter stage. And the same concept with the output capacitor, you actually don't need it for stability, but it does improve transients response. So to simplify the schematic, to simplify this circuit schematic, what you need is only R1 and R2. That's all. You don't need output capacitor and input capacitor. So the same concept with the input capacitor and output capacitor. As you can see right here, you actually don't need the input if it is near the power supply source. Output is also the same. And remember, you don't need to follow the exact value right here because it's only the recommended value for you to pick. But actually, the range of the uh, capacitor can be around like 0.1 to 10 microfarad. So you can choose whatever value from that range. Don't need to be this specific value because this is only the recommended instruction. Okay, so please choose from your available source. No need to follow the exact instruction. Okay, so after the capacitor stage, let's talk about the formula one. So again, we are using the same formula for both ICs. So as you can see, this formula is basically the same with this one. Well, this one is simplified from this one right here. So you have the V reference. The V reference is minus 1.25. So it is opposite with this one. There's no negative sign right here. It's only positive 1.25. So there is the only difference is the minus sign. And again, we don't put the current adjustment in the calculation because based on the manufacturer, they want to control the current to less than 100 microamps. So basically, you can put the calculation, you can put the value of the current adjustment to be around 0. So we can neglect this term right here. So to simplify the equation right now is only like this. So mostly based on the value of R1 and R2 to control the output voltage. Okay, same concept, same concept with the uh, LM337. This is the simplified formula to control the output voltage. Okay, the only difference is the sign value because this is a negative voltage output. Okay, so next we need to take a look about the dropout voltage. So as just like I said before, there is crucial dropout voltage you need to take a look at. So swipe down to page 5, figure 10, dropout voltage. As you can see right here, if your current is at its maximum stage 1.5 amp, the dropout voltage might be around 2.5. So let's say you have 6 voltage input into the IC and the current is 1.5 amp. The maximum output voltage right now is can only like 3.5. So there is significant dropout voltage around 2.5 volt. So this table right here is pretty, this figure right here, this graph is very significant if you want your output voltage to be precise. Okay, so same concept with the dropout voltage of this IC. Swipe down to page 5, figure 8. You can see the dropout voltage. Okay. Okay, so after this, what you want to look is about the diode protection. Swipe down to page 7. If you already included the input capacitor and output capacitor, what you need next is the protection diodes. Take a look at this schematic right here. We can follow the manufacturer instruction to place the diodes. So right now they placing the diode D1, same as mine, and they are using 1N4002. For me, you don't need to follow the exact instruction, the exact value of the diode. You can change it, uh, whatever value you like. For me, I choose 1N4007, which is the only I have, and it still works perfectly. It's fine. So basically, you don't need to follow the exact instruction. You can be more creative in choosing what electronic components based on what you have. So you only need to put the diode D1 if you have the diode C output right here, if you have the capacitor right here, because this diode right here is placed to protect the reverse current when this capacitor is discharging back to the source. So the output terminal of this IC is it just doesn't like the reverse current from this one right here or any short circuit circumstances. It's It's this diode purpose is to create a path for the reverse current to flow back to the input, and then from the input, the current is trying to push back to the IC and escape the IC through the output terminal, and then slowly discharge their energy like this. So this capacitor is trying to discharge the current, so the current flows like this, and it's flow through the diode, enter here, and then go through the IC, and then getting back, same concept, and slowly discharging the current to protect the IC from overheat. And yeah, that's all. So if somehow you have a load right here, if you have a load right here, the circuit is work perfectly like this through the load and back to the source, and the capacitor is discharging, the current goes like this. Everything works pretty normal, but somehow there is short circuit and the capacitor is having no path to discharging like this. The current is trying to push back to the source, and this stage can damage the IC, so this diode is placed to protect the AC, and you actually don't need this diode if you don't have this output capacitor. Okay, if you included this capacitor, you must include the diode D1 right here. The same concept with the D2. If you place the adjustment capacitor right here, you need to also place the protection diode like this based on the manufacturer instruction. For me, I don't put the adjustment capacitor, so I don't need to put the diode D2. Okay, so that's all. Same concept, same way with the LM337. We also have the protection diode right here. Place the diode like this based on the instruction. If you have the output capacitor, then you need this diode right here. If you have the adjustment capacitor, then you must have this diode right here. And again, you don't need to follow the exact value of the diode. You can change whatever you want. Okay.
Okay, after we have a good understanding about the regulators, let's put all the components together. As you might notice, I'm not using the correct capacitor right here, the input capacitor and the output capacitor, because honestly it's not a big deal to change the value. So instead of choosing 0.1 microfarad, I'm choosing 10 as the input capacitor, and the output capacitor is 220 and 220 microfarad. Combined we have like 440 microfarad. So it's not a big deal to change the value of the capacitor. It's just based on my experience, what I like and what I have. Okay, so no need to follow the exact instruction. And yes, I'm choosing 1N4007 diodes right here. Same with this one. So not follow the exact instruction. No need to do that. Okay. Again, actually you don't need this capacitor and these two capacitor right here. I just put it for fun. Okay. Let's talk about this transformer right here. As you can see, I'm using the center tap option. Remember, it must be the center tap. The ratio is about 230 divided by 30. The ratio of the primary coil and the secondary coil. Before, I leave this pin unconnected, but now I'm using it. And this pin right now is the reference point, 0 volt. So the purpose of the reference point right here is scale the voltage and create the negative voltage. Basically, as you can see right here, the transformer stage, this is the input stage. We step down the voltage into suitable range using diode to convert the voltage. And then we using capacitor like this to smooth out the voltage. And but this time the 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 voltage difference between two terminal is pretty high, 40 volt, without a reference point right here. So without a reference point right here, the voltage difference is 40 volt. And then when we have the reference point in the middle, we can scale down the voltage and using the regulator to control the voltage. So one terminal is 20 volt. So this terminal is 20 volt, and this terminal right here is negative 20 volt. So we're just using the reference point right here to create the negative region, okay? So without the middle pin connected to ground, there won't be any reference point for us. Okay, so pretty simple, okay, right? I will show you the simulation stage.
Okay, so this is the simulation circuit on NI Multisim. So this is how I place the components. Oh, so just take a look at these right here. Originally, this software doesn't have LM317 IC and LM337 IC. So I just had it on the internet. I will leave a link for you to download. But actually, the behavior of this IC is not correct like we have in real life. Okay, remember? So let's test the IC we have right now. The output voltage is maximum is around 17 volt and minus 19 volt. So these are the maximum output voltage, but in real life I have something around 19 volt, so the simulation is not correct like I have in real life. Okay, so this is just for reference. You actually really don't trust the simulation at all. Okay, so when I adjust the potentiometer right here, I can also adjust the output voltage. As you can see, same concept with the negative region, the negative voltage. I just can uh, adjust the potentiometer right here, and then the output is fluctuating. Okay, so pretty easy. But as you can see right here, I'm not using 4,000 and 700 microfarad. Why? Because somehow my simulation is not working when I choose this value. Let me show you. Uh, like you can see, it's not working because, as like I said before, I had it on the internet, and this is basically just a math box. So it might doesn't work with this value, and originally this software doesn't have it. So only for reference, I figured it out. I choose the 47 microfarad, and somehow it worked like this. So I just figured it out. Very lucky for me. So in real life, this one is 4,700, not 47 like I have on the software. Okay. And next we have the capacitor right here. I choose 10 microfarad because actually you can choose whatever value you want. This capacitor actually doesn't need it in a simulation. And for the output, I choose 470 microfarad. Pretty big value, but it's okay. It still worked. So I just leave it there. 470, like I have in real life. And so I have the diode. The diode is 1N4007, not 4N4002, based on the manufacturer. And I have potentiometer right here, 5K, and the R1, R3. Okay. Diode protection. Okay. Right. So let's talk about the transformer stage. So we have the input voltage from the source. 230 volts, which is around um, 324 volt peak. So this is the output voltage peak from the source, and this is after the secondary stage of the transformer. As you can see right here, around 21 volt peak, which is around 15 volt RMS. So the transformer ratio is about 230 and 30, the ratio. So this is the ratio based on what I have in real life. Pretty simple. So yes, you see the arrow. There's a lot of arrow in here. The arrow is based on this math box right here. This doesn't work perfectly, but it's still, you see, the voltage is stepped down from 300 to around 20. So this is how it looks inside the circuit. So at the first stage, we have the transformer. I put the oscilloscope right here. So the ratio for the oscilloscope is around 230 and 30. So this is the ratio close to my transformer in real life. And so this is the transformer. This transformer is trying to step down the voltage from 224 volt into around 20 and 21 volts peak. So this transformer is pretty much the same like I had in real life. And so the next stage, the filter stage, you can see this is the ripple voltage from this oscilloscope right here. So this is the stage, the filter stage, pretty much the same with what I'm draw on the paper before. So the ripple voltage keeps us the voltage around 20 to like from 19 sometime to 20, as you can see. So 19, 20, so like 19 and 20. So the ripple voltage is pretty significant, around 1 volt. And so the last stage, the output voltage that can be adjusted right here. So as you can see, without the middle pin, I will show you. So I delete this middle pin right here. There's no connection to the ground reference, and right now the ground reference is at this point right here. So this is how it's gonna happen. So there is the voltage difference from this terminal to this terminal is around 40 volts. Just like I said, the real voltage is around 37 because there are voltage drop between these IC. Okay. Okay, so instead of you have two, one is positive voltage and one is negative voltage. Right now we only have one positive rail because the middle pin doesn't work to to be the reference point. So instead of the reference point is right here in the middle of the 40 volt, is now right here at the bottom of the 40 volt. Okay, so let's put it all together for you to see. Okay, and where's the ground? So the ground, put the ground again, and connect to the ground. Okay, as you can see, so we already scaled down. So this is our voltage.